Assalamualaikum and good evening to lecturer and my friends. Welcome to our group presentation for student-centered learning SEL project. Our main theme for the project is momentum analysis and flow system. Our lecture name is Dr. Adi Azrif bin Basri. Today we would like to present about the wind turbine and its efficiency in consideration to the momentum analysis of airflow. So we go to the first part, which is the introduction. Wind turbines are primarily used to generate energy using the wind. Aerodynamics, therefore, is a very important aspect of wind turbines. As with the most machines, there are many different types of wind turbines, all based on different concepts of energy extraction. Although the details of aerodynamics are highly topological dependent, some fundamental concepts apply to all turbines. All the turbines can generally be grouped as either lift-based or drag-based. The former is more efficient. The aerodynamic force used to extract the energy is the difference between those groups. The most common topology is wind turbine with horizontal axis. It is a very good performing lift-based wind turbine. It is therefore a popular choice for commercial applications, and a lot of research has been applied to this turbine. This design method uses the theory of blade element momentum, which is BEM, and the second one, which is blade element theory, to complete the design and can be executed using a spreadsheet and lifting and also the drag curves for the aerofoil chosen. These are the some of the example of wind turbine. The first one, which is the Darius wind turbine, the popular lift-based alternative, and the second one, which is the Savionis wind turbine, and it is commonly the common type of drag turbine. So that's all for my part. So I pass to my second member to continue the presentation.
Hello, my name is Ishan Mitra Haldar and my metric number is 201390. I will start with the literature review. One of the most abundant sources of renewable energy is wind. Today, a considerable amount of resources are being utilized for research on harnessing the wind energy efficiently. This project will examine how the airflow affects the wind turbine's energy and try to find ways of increasing the efficiency in consideration of momentum analysis of airflow. I will start with the first question: why wind turbine and not any other kind of turbines? As early as 3000 BC, people used the wind energy in the form of sailboats in Egypt along the river Nile. So it has been in used for a long time. It is clean and renewable. It is quick to set up, and we can also do some agriculture in the same area. But there are some problems also: noise pollution, harmful to wildlife like birds, and it might be slightly costly too. And this table actually shows that the wind energy costs 4 to 10 cent per kilowatt, which is quite costly in comparing to hydraulic, but quite cheap comparing to the solar energy. Now, I'll proceed with the wind turbine. Wind turbine there are mainly two kinds of wind turbines. One is the hot and the another is the watt. The watt means vertical axis wind turbine, and hot means the horizontal axis wind turbine. And this study focuses on horizontal axis wind turbine. Uh, this slide shows some components of the horizontal axis wind turbine, and we can see that there are blades, rotors, low speed shaft, gearbox, controller, and many other things. But this work will focus on the rotor blades, and the main work method of it is by using the wind flow and using the lift and drag effect. Why this blade design is important can be surely seen from this slide. We can see that at first, when we started harnessing the wind energy, the peak efficiency was only 16%, and now at 20th century, the hot can produce 50% efficiency. Moving forward, we'll go in depth of how we can design the rotor blade. We are going to use the BEM, which is boundary effect method to design this wing, and the main equation that we are going to use is the Betz optimization equation. But to use it, we need to first know about the flow around the blades, and this slide shows the flow region of turbulent boundary layer and the contour of the time averaged streamwise velocity component. And then we can see in the left that it is showing the streamwise turbulence intensity and normalized kinematic vertical turbulent momentum flux, and we can use all this in the flow around wind turbines equation. Then we can use that one in the Betz optimization equation and design the blade. But there are other concerns too. Depending on the number of blades, the shape might change, and that shape will depend on the lift to drag ratio, which is being showed in this slide. There are smart blade designs too, and it actually uses the concept from the aircraft wing, and we can see that there is active tape, then active twist and active flap, and the graph on the right actually shows that how it actually peaks the efficiency by using all these into the wind turbines blade. And lastly, how do we ensure ultimate efficiency? There are three main things that we need to uh, always remember: that we have to reduce the angle of twist, we have to linearize the chord width, and lastly, we have to reduce the number of differing aerofoil profiles, and that will give us the most suitable wind turbine blade with most efficiency. That will be all for me, and I'll proceed to the next presenter.
Okay, my name is Nurul Christina, and my message number is 202750. Okay, for my part, I will explain about the working principle of wind turbine. Uh, sorry. Okay. First of all, the majority of wind turbines consist of three blades mounted to a tower made from tubular steel. At 100 feet or more above the ground, the tower allows the turbine to take advantage of faster wind speeds found at higher altitudes. The turbines catch the wind's energy with their propeller-like blades, which act much like an airplane wing. When the wind blows, a pocket of low-pressure air forms on one side of the blade. The low-pressure air pocket then pulls the blade towards it, forcing the rotor to turn. This is called lift. The force of the lift is much uh, stronger than the wind's force against the front side of the blade, which is called the drag. The combination of lift and drag causes the rotor to spin like a propeller. Okay. This one shows the inside part of the wind turbine. First, a series of gears increase the rotation of the rotor from about 18 revolutions a minute to roughly 1,800 revolutions per minute, a speed that allows the turbine's generator to produce AC electricity. A streamlined enclosure, usually including the gears, rotor, and generator, are found within a housing called the nacelle. Next is another key component is the turbine's controller that keeps the rotor speeds from exceeding 55 miles per hour to avoid damage by high winds. Um, an anemometer continuously measures wind speed and transmits the data to the controller. And lastly, a brake, which stops the rotor mechanically, electrically, or hydraulically in emergencies. Um, this picture shows a clearer version of the whole system of the wind turbine. Okay.
Hello, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Syafiq Akib bin Ghazali. My metric number is 202791. Okay, this is our 3D model design. I have created two design. for the first design is common wind turbine, and the second design is for the new prototype wind turbine. That you can see the difference between the blades. Okay, next slide. Okay, this is the orthographic drawing for the common wind turbine. That you can see the meter. Okay, next. Okay, this is for the new prototype of wind turbine. Next slide. Okay, characteristic blades for the common wind turbine. Okay, for the common wind turbine have a flat and the straight blade that will give less efficient and then will give much more drag for the wind turbine. That will give less efficient for the wind turbine to rotate. And then second is less aerodynamic profile. That will give poor lift to the wind turbine. Okay, for the new prototype wind turbine blade, the blade is slightly curved and twist. That will reduce the drag force and also tapering in along its length, producing the most efficient wind turbine blade design. Okay, for second, better aerodynamic profile will give more lift to the wind turbine to rotate and will give a higher efficiency and more power energy will get. Okay, thank you.
Okay, my name is Nasabrina. My metric number is 203138. So there are two types of.
Syafiq, kau kena mute dah Syafiq. Kau punya kamera suka sangat keluar.
Okay, my name is Nasabrina. My metric number is 203138. So there are two types of wind turbines, which is horizontal axis wind turbine and vertical axis wind turbine. Next. So for the comparison of the horizontal axis wind turbine and vertical axis wind turbine, we go first for horizontal axis wind turbine. First, needs the wind to flow at a right angle to the blades. Next, convert more of the wind's energy into useful mechanical motion because the blades are perpendicular to wind direction. And the last one is tall tower and long blades work well only in wide open spaces. For the vertical axis wind turbine, runs well regardless of wind direction, capturing energy from the wind only on the front side and the rear part of their rotation. And the last one is compact and can be placed on building rooftops and other urban locations with fewer restriction. Next. Improvement. On our project, we specified the improvement for the blades, and the criteria of the improvement of the blades is size, length, shape, and angle. And for the further explanation on our report.
So, Assalamualaikum. My name is Muhammad Yunus bin Shamsobari. My metric number is 204686. So, I'll be talking about recommendation for our project. So, based on what we have found, there are a few recommendations to make. Firstly, we should use larger blades on the wind turbine because larger blades allow the turbine to capture more of the kinetic energy from the wind by moving more air through the rotors. Using a larger blade, we can increase the efficiency of the turbine. Secondly, larger blades and longer blades will increase drag. So we can reduce this drag force from larger blades by bending or twisting the blade and also tapering it along its length to produce the most efficient wind turbine blade design. Lastly, an angle of attack of the blade also affects the efficiency. a larger angle of attack will decrease the amount of lift that the blade makes. So there is an ideal pitch angle of the rotor blade that will create the best rotation and efficiency. Modern wind turbine rotor blades are actually designed with a twist along their length from a very steep pitch at the root of the blade and a very shallow pitch at the tip of the blade to improve efficiency. So as a conclusion, thank you to Dr. Adi for watching our presentation. For more detailed explanation and information on our project, you can view our report. So once again, thank you, Dr. Adi, and Assalamualaikum.